We have seen the animations of charge and current moving along wires or freely in space. We have written expressions for the fields when the charge moves uniformly at constant velocity. Now we are going to see the other case, which is the most interesting for us if we are working on communication systems, which is the case of a charge that is accelerating. Why? Because this is equivalent to saying that we have a current that is changing in time, a current that is carrying information. So when a charge carries information, in fact, in the antenna is just subject to acceleration. And in the animations you saw this case, especially in the charge when it was suddenly accelerated, you saw that the transversal field appeared. The charge is at this point, and now we have a trajectory, but this is the change with respect to the previous talk, that now we need to know the acceleration, and the charge may move along a complicated path. For the observer, we have exactly the same reference. We have the distance, the radius, the vector radius. Here we have the projection, but now the projection, one has to be very careful, because with the information we have at this point, which is the acceleration and the velocity, the only thing we can do is to guess where the charge would be if it was moving under uniform motion case. That means under constant velocity. And this is something that we can do, and then we may say that this is a virtual point or a projected point where we may think the charge is if it moves with constant velocity. But in real life, the charge is not there. The charge is somewhere else, probably at this point, because the trajectory is not this one. But this is useful to write expressions, because now we have here the virtual or the suspected or the projected point, and we can use the same notations we used before. Now, the only change with what we saw before is that here we put the V to denote this as virtual. This is where we may think it is, but this is not where maybe it is. There are cases for this that are simple to reference. For instance, you all know that the stars in the sky are a fixed point, but when the light goes through the atmosphere, it suffers refraction and it changes in some way its path. To our eye, when we look, we just see where the light is arriving to our eyes. And at this moment, we think that the star is just in a certain point. As time goes back, this is why we see the star wiggling around. It's not the star, it's just the direction of arrival. This is like to say that the star isn't there, but to us, is if it were there. The expressions in this case have expressions for the uniform motion case plus the important one. Now here we use two things to denote them. We call this the induction or near fields. And we call those fields the radiation or far away fields. Sometimes we use different names for this. The main difference is that this one will fall off as 1 over the square of the distance, and this inversely with the distance. And this is the magnetic field. And those are the expressions for the electric field. And in this case, this is just the fields that one may in some way detect in a short range of the charge, and those are the faraway fields. Those are the ones that we can see in the propagation of electromagnetic waves. Two cases. Low velocity, in this case, compared to the speed of light. Then we can simplify the expressions. and we just forget about the induction fields, the near field, and we just concentrate on the faraway fields. And here you have the expanded value for the field. We have the charge, we have the distance, the unit vector for the position we are talking about, the vector, the cross product, and the acceleration. And we also have the magnetic field. And if you look at those two expressions, you will see that they are quite similar, except for this term here, this one, and there's another cross product here that is not in this. But we can rearrange everything in there in a compact way and say that the field, the electric field radiated by this charge is related to the magnetic field through a simple expression, is the product, the cross product of the magnetic field and the unit vector in this direction. And then we have here an impedance that will just make the correct units for this. But also we can say in exactly the same way that the magnetic field is proportional to the electric field, and we have the inverse of the impedance here. And we have here this unit vector here. This is just the TEM wave. This is a transversal electromagnetic wave. And this is the kind of waves we encounter in communication systems or in the case of the light. Sometimes we use the induction field or the magnetic field intensity, and they are just related by the permeability of the medium. The parameters involved in those expressions are the permeability, the wave impedance, and the wave velocity, which is the speed of light. In this case, the expressions are written for vacuum, that means for the space that is empty. In our communication systems, in the case of the atmosphere, in the case of the air, the expressions are exactly the same, there is no change. Now, to simplify this case, let's rewrite the expressions in terms of the acceleration and try to extract some information on more interesting cases, as maybe antennas. This is just the notation. We have the charge moving with acceleration in this direction. We have this angle, the unit vector in this direction, which is the direction of propagation. If you want to show with the finger, my finger is pointing in the direction of propagation. Then we have an electric and a magnetic field that are orthogonal to one another and to the direction of propagation. This is why this wave is called transversal, because the electric and the magnetic field that are being combining and oscillating in synchronism are pointing in those two orthogonal directions. When you write this double cross product, at the end you just get the acceleration times the sinus of this angle. This is a simple expression. And the power density that we call formally the Poynting vector, which is just the product of the electric and the magnetic field. Just to make a simile, this is like to say that the power in an electric circuit is the product of the voltage and the current. The units in this case are watts per square meter, per cross surface of the wavefront. And those are the expressions. That means that the power density follows the sine square law. This is important to remember. And these two cross products give you a new vector. So it's telling you that although the electric and the magnetic field are in the plane perpendicular to the direction of propagation, they are pointing in this direction. Okay? The power is being transported with the wave. It's traveling along the space, following the path of the wave. If you look at the expression, it's simple to say that if the charge is moving in this direction, an observer in this direction will see nothing because this angle is 0, while an observer in this direction will see maximum. And the plot is just like this donut that has two circles of equal amplitude on both sides. In fact, in space, this is just a general expression of something that really will look like a donut in the full space. Here you have the charge times the acceleration. For the harmonic case, the charge times an acceleration is similar to the product of the current times the frequency and the length, like a derivative. And if you look at this expression into the antenna books, you will find it. And you will find it when trying to study a dipole antenna. A wire antenna is just a long wire that is radiating. And wires radiate in this way. And it follows this basic law. Just to summarize the expressions, we can write the power density that is carried by this wave and the same law. And here we just write the power per unit solid angle. That means the power that is contained in a cone, not on the piece of surface. We also have a radiation pattern that you saw is sine square, is this plot, that tells you in which direction we are producing the highest value for the power density, for the power radiated by the antenna. This is important in the antenna because you normally want to align the antennas in such a way that the maximum power is directed towards the receiver's. In mobile communication systems, with our mobile sets, this is quite difficult because we have the head, we have the antenna, and it's hard to point it. So in this case, this is not really easy to align, and we never care about this. The total power radiated by the charge could also be found just by integration in all directions, and it gives you this expression. And this is just the value. It's proportional to the square of the acceleration. That means the higher the acceleration, the higher the total power radiated or lost by the charge. This is an expression that is very well known. Larmor, the man that introduced the electron into the picture of electromagnetics. And this is the expression he gave for the power radiated or lost by an electron that is being accelerated. So this is just a complete set of expressions for this. We have just, in this case, found the basic aspects of charges and see how they accelerate and produce fields in space. We will exploit this later on in the course.